Thank you very much. Really? I cannot wait. Oh, thank you. I feel like it's too long. I just like changed the layers to my mouth that I wanted to. I'm gonna try to get it cut here. I'm gonna have like this wide span, like right here, and I want like at least
Okay, I'm gonna get started. Okay, hello everyone. Hello. Hi, thank you. Welcome to Astro on Tap. We have a special Astro on Tap tonight. I say that before every Astro on Tap. We're going to have two really fantastic talks. The first one is Insights from Insight, newest results from the Martian interior, and that's by Rudy Garcia. And our second talk of the evening will be Raising Esteem, Bringing Astrobiology to Incarcerated Youth, and that is by Samantha Gilbert-Janizek, and that will also be a fantastic talk. I'll introduce both of the speakers before they come on, but first, of course, we're going to do trivia. So how this works is I will go and put 10 questions up on the screen one at a time. You'll have 30 seconds apiece to look at the question and write down your answer. After I go through all of the questions, I'll go back and then show them again for 15 seconds apiece, and that will be your last opportunity to put your answer down. After that, we will collect the trivia sheets and get our first speaker of the evening set up. While he's speaking, we'll grade your trivia sheets, and then we will announce the trivia answers and the winners after his talk. That'll be followed by the second talk of the evening, and after all the talks are done, if you won trivia, then you can come get your prize. Okay, sound good? Awesome. Okay, so remember, 30 seconds apiece, first time through. Okay, did everybody get their trivia answers down? Hello? Hello? Did everyone get their trivia answers down? Okay, that's good. For those of you that said yes, you can bring your trivia sheets up to Sam and the golf pencils, please. We want the golf pencils as well. We're going to get our first speaker ready, and I'll be right back. Thank you.
The end fell off, sorry.
Oh, no worries. Thank you. Where is Rudy? I thought he was joking. I am going to kill him. Should I start chanting Rudy? Oh my God, should we start a Rudy chant? Oh, hi, baby girl. I missed you. I missed you.
Is it on?
No.
The people in front of me didn't know what they wanted.
I was so tempted to start a Rudy chant. I was about 10 seconds away from it, just so you know. Here.
It's very hot.
While I introduce you, you can put this on.
Okay. Gracias. What the? Oh.
Do you want to?
Can you hold these? Thank you.
Here.
Oh, wait. There. All good. Sorry.
Okay. Hello again. So at this time, it is my pleasure to introduce our first speaker of the evening. So our first talk is called Insights from Insight, Newest Results from the Martian Interior. Our speaker of the evening is Rudy Garcia. You may remember Rudy was supposed to speak 2 months ago and he got sick. And so it is my absolute pleasure to bring him back this month to give his talk. Some of you may know Rudy from past Astro on Tap talks across the last couple of years. He's a phenomenal public speaker. He's a grad student in the astronomy department and also one of my 2 office mates. Yes, that's what you're best known for. I'm just kidding. Just kidding. Okay, so with that, please come up here, Rudy.
Oh. Do I need this if I'm speaking into this?
Both.
Oh, both.
That's for
for the video.
Yes.
So it's not going to amplify.
No.
But this will Okay, we're good. All right. Oh yeah. Gracias. So let's talk a little bit about Mars. So my talk is called Insights from Insight. Newest results from the Martian interior. So inside Mars from the InSight mission. What kind of insights might we get? And the goal of my talk here is I want to kind of contextualize this mission. Something that kind of gets me a little, not frustrated necessarily, but I feel like in the news, we see all these news articles about NASA missions landing or successfully reaching wherever they're supposed to go. And then we never hear about them again, except maybe like 3 years later when NASA says, hey, we're broke, we can't fund this mission anymore. But there's a lot that's going on inside those 3 years. And so a big goal of mine is to kind of show y'all what this actually looks like. What are our tax dollars actually going to do over on Mars? And the other thing I want to show is that science is really messy. This is something that I've been learning over the past 5-ish years, that science is a messy endeavor. It's very difficult, and it's not very pretty. But I figured where else than here to see where how the sausage is made. So let's start with InSight. What is InSight? It's a little lander on Mars. This is an artist's conception. It's got two different parts to it, mostly. It's got the core lander, and then this little guy is a seismometer. And most of this is going to be about the seismometer on this little dude. Landed on Mars in 2018. Maybe you might remember there's some news articles at the time, and it just recently, I believe, finished observing at around 2020, 2021. Fun fact, a lot of the times when NASA missions end, it's not because something breaks, it's usually because NASA doesn't have the money to keep funding the scientists to do it. So this is a classic NASA right there. But really classic Congress, am I right? So as I learned, this is the very first seismometer on Mars, but we've been trying for a long time. In fact, for 50 years, we've been trying to get a seismometer on Mars. The ones on Viking didn't work. Well, the one on Viking 1 didn't work. The one on Viking 2, turns out Mars has a lot of wind, and that's really loud. And we didn't know that in the 70s, and that really masked any sort of Mars quakes we wanted to observe. So rip to those. I learned about these two missions, Measure. Okay. I thought it was like Misur or something. I don't know. I see it now. So Measure was an ESA-led mission, the European Space Agency, but NASA was probably going to put some money to it as well. It would have put 16 seismometers on Mars. This was in about the 90s. But then it turned out to be too complicated. It turned out to be too expensive. And if there are any engineers in the audience, maybe you're familiar with this kind of classic development cycle of we're going to do this huge thing, and at the end of the day, we end up doing this really, really tiny thing. So not enough money to put seismometers on Mars back then. 1996, Russia tried to put a seismometer on Mars. That crashed in the ocean. Actually, I assume that the Earth ocean, now that I look at that, there's no Mars ocean. And then Netlander's my favorite because that's the ESA-led mission. I misspoke there. ESA would have led it and NASA would have helped a lot, but NASA had some mistakes. Lots of Mars orbiters crashed, and so Mars was kind of taboo. So NASA pulled out, and ESA was like, well, we can't do this without NASA's budget. And yet again, it was just too expensive to send a seismometer to Mars. So I show this because I really want to show, science is messy, right? We haven't put a seismometer on Mars in the past 50 years, partially due to technology issues, but mostly due to socio-political economic issues. And so this is a really classic science. It's something we learn about a lot. As you read through these things, Texas doesn't have an LHC because it would have been too expensive to build it in the 90s. So now my grandparents have a giant 3-mile wide hole next to their house. So is what it is. But we did finally put a seismometer on Mars. And the goal of this seismometer is to help us tell the story of Mars. What is Mars? What's it doing? What has it been doing in the past? And this is another example of how science isn't usually done with these big sweeping changes. We know a lot about Mars, but there's a lot of sort of clouds and things that we just can't quite understand. The things we know are kind of wide, but they get really fuzzy along the edges. And science is all about kind of investigating that fuzz and trying to, put our glasses on and see things a little more clearly. But it's not as simple as, one person coming up with this idea. In fact, the Mars' story, Earth's story, any large scientific story or narrative is really the coalescence of decades of messy observations, discussions, and growth. Much like any of our personal stories is a result of the same. There we go. So in order to tell the story of Mars, give context for what InSight was doing, I always love showing these maps of planets. So this is a map of Mars with some of the most relevant regions labeled. The ones in red circles are the ones I'm going to talk about today. InSight landed around this Elysium Mons. These are some mountains. That's what Mons means in Latin. And then there's the Tharsis Rise and the Valles Marineris, this huge, almost Grand Canyon-esque structure on Mars, and these gigantic volcanic mountains, one of which is Olympus Mons, the largest mountain in our solar system. So these are the most relevant areas, and they're very interesting. And a lot of Mars science kind of tries to explain what's going on in these areas. So the story of Mars is the story of its surface-altering processes. So when we look at Mars, what we're really doing is looking at different sections of Mars that preserve what was happening at Mars way back in the day. And so here, starting from the earliest time period on Mars, the pre-Noachian period, all the way up to today's period, the Amazonian. There's your answer. We have here a kind of interpretation, although this is from a 2012 article, so it might be a little out of date, but an interpretation of what might have been happening on Mars throughout this time period. Most key are these valley networks. That's where there's a lot of rivers on Mars. But we get these kind of interesting outflows on Mars later in its life as well. These are not we don't think these are persistent water forms. We think these are more just one-time gigantic floods, and then the water all froze up or something like that. But then we've got these basins. Those are all giant meteor impacts or asteroid impacts. And then in the brown here, we've got the volcanism, which is heavily defines Mars. So we've got this kind of Tharsis region is still pretty young, but it's been active for a long time. And then the Elysian region is also still a little active, but not as big as Tharsis. So the question is, what's going on here, right? How do we kind of explain how all of these things come together and tell us what Mars has looked like over the past 4.5 billion years? We can do this with some satellites. Right, we can look at how Mars's surface has changed, but then we can also look at the minerals on Mars. So this is kind of a newer thing that we've been able to do with some of the more recent mid-2000s satellites. These can tell what kind of minerals on Mars, and using a bunch of smart geology stuff, we can kind of understand how old these minerals are and what happened to Mars during the growth of these subsequent mineral eras. And so we have these the surface eras and the mineral eras, and they have slightly different names and slightly different timescales, but they're kind of two different lenses of looking at Mars. And these are things that we've coalesced to kind of tell the story of Mars. But it's not all, we don't all understand everything. There's still, like I said, a lot of fuzz at the edges. There's still a lot of unanswered questions, and that's why we send missions like InSight. That's why we're still sending things to Mars and still hoping to send things to Mars, is to try and answer some of those unanswered questions. So for example, a big one is if Mars had tectonic plates in its past. So Earth has tectonic plates. We're all sliding around on these plates. Venus doesn't have them. Mars doesn't appear to have them, but maybe it did in the past, and that's got a lot of implications for what might have happened inside the planet and on its surface. We can ask when Mars's magnetic field shut off. We can see that it's got fossilized, it's got this remnant magnetic field that was kind of sealed into the rocks back when they were magma, and it doesn't have one now. How long ago did that shut off? And that's relevant to Mars because we think that the magnetic field on Mars has something to do with when Mars lost a significant amount of its atmosphere. And so the question is, when did it lose the atmosphere? What was the time scale on that? Did the magnetic field get lost before or after that behavior? And then we want to know what's happening inside of Mars. What's fueling all these volcanoes that are still going on, some of which are still going on. And of course, always the motivating question is there or was there ever life on Mars? And any time we can answer any of these questions, anything that helps us characterize the environment can help us understand any future measurements we might make of potential life or fossils or anything like that. So these are all still very, very relevant questions. They're all very, very up in the air. So with that, we got to figure out how we can answer those questions using the InSight mission. InSight has 3 instruments, SACE, RISE, and HP cubed. SACE is just a seismometer. RISE does some really complicated stuff I really don't understand, but it's just, yeah. I tried to read the paper, but I really couldn't understand it. But it just measures how Mars wobbles, I guess. So Mars wobbles, and it can learn more about the core of Mars that way. And then we got HP cubed, which can measure the heat flow near the surface of Mars, but a little underground. And I'll talk about that one at the end. So now I'm going to talk more about what these instruments measured, right? They're sitting there on Mars for 2 or 3 years. What's going on? Firstly, we measured a ton of Mars quakes. I'm probably going to slip and call them earthquakes. Whatever. It's still called geology when it's on Mars. Like, be a pedant about it if you must. But I also call them events because that's actually what most of the papers call them. But what does this look like, right? So ultimately, InSight's seismometer measured, I want to say something like 1,300 individual Mars quakes. Now you might be asking yourself, how does Mars have Mars quakes if it doesn't have tectonic plates, right? Here in Seattle, we're due for a really big one because we're really close to a plate boundary. Tons of earthquakes happening in Japan and Chile, right? Anywhere on those plate boundaries, you're bound to get some huge motions. Mars does have Mars quakes. They're not very strong. See, tectonics is a fancy word that just really means how the planet is being deformed. Plate tectonics, plate is like an adjective here. It's just like a type of tectonics. But really, you can have tectonics without the plates. Oh, my slides are a little out of order. That's fine. So Mars, we see, is active. It is more active than the moon, which is down here. You can't see it that well. In yellow is like Mars. On the y-axis, it's the number of events, the number of quakes. On the x-axis, the magnitude of the quakes. You can see Earth is, very, very tectonically active. Mars is less so, but more than the moon. So there's stuff going on Mars. And interestingly, science is full of these like unexpected, unknown unknowns. We saw a lot of these weird high-frequency events, really, really weak Mars quakes, but there's tons of them. And this was kind of an open question, like a mystery for the first year or two after InSight started getting data back to us. And we answered that mystery, and I'll go into that as well. But what's fueling this is not tectonic plates, really. It's just deformation. See, when you have like anytime rocks break, they're going to form faults. A fault is like a fancy word that just means like a crack in the rock. And so if you pull like a sheet of rock apart, it's going to crack, and you're going to end up with these extensional normal faults. If you push a sheet of rock together, you're going to end up with these reverse faults because it's also going to crack. On Mars, and of course when these cracks form, and when those bunches of rock get really stuck, eventually they get unstuck, and the result is an earthquake or Mars quake. And so again, this is why we should all have like a little earthquake preparedness kits, because in Seattle, our tectonic plates have been really stuck for like a long time. So there's a lot of energy just really, really stuck there, and that's gonna come out pretty big. I think about this a lot. I don't have a preparedness kit. But here on Mars, we can see a map of all the different faults on Mars, the different extensional fault where the whole planet is getting torn apart, and the different compressional faults in blue where the planet is getting pushed together. Most evident here is the Tharsis region, all those giant volcanoes. Those volcanoes are so massive and so heavy that they've actually cracked the whole planet beneath them. That's why there's this whole like sort of radial network of faults kind of like coming out of where those volcanoes is, because they've just kind of, if you stomped on a block of ice, it would crack similar to this. And so this is what InSight is measuring. It's measuring movement in some of these faults. And the question is, which of these faults are the most active? So this is where seismology comes in, and I don't understand seismology. Everyone I've met doesn't understand seismology. It's like a real like magic science. So I'm gonna try and give the quick 1-2, but essentially we're measuring waves from earthquakes or Mars quakes. When the planet quakes, it shoots out waves. Some of them go like this. Those are the P waves, the pressure waves. They're kind of like sound. And some of them go like this. And those are the S waves, or the shear waves, the up and down waves. What's funny is that S waves cannot travel through liquid. You try making water go up and down. It's not really possible. You can do this to water and it'll go like that, but you can't, schwip water while you're inside of it. And that tells us something about the core. If the core is liquid, then you could see these S waves, they just can't go through it. They turn into P waves, but they don't, you don't see the S waves on the other side. So that's a little foreshadowing for some of the magic seismometry can do. So here we can see there's these low frequency events and these high frequency events. So these high frequency events are the kind of like weird ones that we don't really see on Earth or the moon. And those are kind of echoed in the crust, whereas these low frequency events are more analogous to earthquakes, and they go through the Martian interior. And so these are really useful because they help us probe what's going on in Mars. And so this is the key with this seismometer. It sits there, it waits for these Mars quakes to happen. We can identify where those Mars quakes are, and we can learn more about what's going on inside the planet. So refinement of location techniques let us trace some events to the, wow. You can tell I haven't talked to non-scientists in a while. But what this basically means is we're trying to figure out, the first thing we want to do, the first seismic magic we want to do is figure out where these Mars quakes are happening. And there's a lot of fancy things they can do. I'm not going to get into it. I also don't really understand it that well. But essentially, a lot of them occur right here. This yellow triangle is where the lander is. And this green line is this dichotomy on Mars, which is kind of interesting. So if you notice, everything north of this green line is very low and flat, and everything south of this green line is very tall and rugged. And we don't really know why this is. Why does half the planet look like this and the other half doesn't? And hopefully, if there are some interesting Mars quakes around this dichotomy, we can learn more about what's going on. What is this like barrier? What does this boundary look like? And so I wanted to show this because I think this is also evidence of how science is messy. There's a lot going on in this figure, but the only thing important to realize is part A shows like prior knowledge, like what the first analysis of events, where we thought they might be. And so this red line gave us like somewhere along this red line is the very far away Mars quakes. It's very easy to find the very close ones, but there are a few far away ones, distant ones, and they're somewhere on this red line. And then a year later, some people did some even more like magical science, and they found out that the distant events come specifically from this area and this area. So again, science is kind of messy, right? Like we make some guesses, we're probably wrong, and then a year later, someone corrects us. And they did a good job, but we did a good job for making those initial guesses as well. We'll see that these distant events occur mostly around the Valles Marineris, so that giant like Grand Canyon looking thing. That kind of makes sense. It's like a giant canyon. There's probably a lot of like rock slides, a lot of like the Mars, the Earth there is very unstable. So that's probably resulting in a lot of these as well. By far, most of the events, I'd say like 90% of the events, come from this one tiny region on Mars called the Kerberos Fossae region. This is a crack in Mars that is not that big, actually. I think this is like 30 kilometers across, maybe. And basically what's happening there is the planet is cracking open. There's a strong force pulling the planet apart, and that's tearing it open and causing a valley to form. I actually just came back from New Mexico like a week ago, and this is very, very similar to the mechanics of the Rio Grande Rift Valley, which Albuquerque is in. If you've ever been to Albuquerque, that whole area, it's kind of like the exact same thing that's going on Mars is happening there, including what we learned from the seismometry, these like magma columns right below the valley. So right underneath this valley, there is active magma just sitting around making cracks inside Mars because it's so hot, it's kind of cracking and popping the rocks around it. And we measure a lot of those as very minor earthquakes. And you can kind of see the same thing in New Mexico, at least according to some paper from 2010. So that might be old. And then finally, I just want to talk real quick before I move on about the biggest Mars quake. This is magnitude 4.5. So Mars has nothing on Earth. We've got much bigger quakes. But this is the biggest one, and it's occurring very close to that crustal dichotomy, which this line is showing right here. And this is happening because the planet is squishing into itself. So as the planet cools down, it squishes. You know, anything that cools kind of like contracts, and this is causing lots of cracks in the planet as well. So this is pretty interesting because this is going to tell us more about what's happening at this sort of boundary on Mars between the really low north and the very high south. Some other magic with seismology is that we can measure the speed of those waves that occur inside of the planet. And somehow that tells us what the inside of the planet is made out of. So here, there are these like fancy pants models that tell us how fast the wave is traveling, right, 2 kilometers per second, as a function of depth. So we can see that there's this, and then there's this huge change here, and all of a sudden the wave is moving faster between 10 and 20 kilometers. When we see that huge change, we assume that that's due to a different compositional layering. So it's like this is one type of mineral, this is another type of mineral right here, where the earthquakes are going at like 2.5 kilometers per second. And this is another one where they're going at like 3 kilometers per second. So this is some other like fancy, weird stuff we can learn about Mars. And what's really cool about this is we just sent the seismometer there. It just listens, right? We're not really doing anything, and yet we still get all of this information about what's going on inside of the planet. This even tells us how thin or thick the crust is on Mars. So this is a very classic dilemma. Is the Mars crust thick or is it thin? And this one result came out, I want to say in 2021, where the scientists looked at the seismometer results and they said, hey, it can either be thin or it can be thick. It really depends on what assumptions you make. And interestingly enough, just 1 or 2 years later, some other scientists made some more assumptions and we got more data, and it turns out that the crust is thick, it's not thin. And so this is just another example of how things change. Even in only 2 years, we went from this kind of it's either thick or it's thin, the crust of Mars, into this idea that it's probably pretty thick. And I think this is kind of interesting. The way that these people did it is they kind of took some of those simpler assumptions that the first group of scientists made, and then they kind of like made them a little more complicated. And this is just classic science, right? We start with these really simple assumptions, we do our work, and then we get a result and we say, here it is. And then a few years later, we add some complexity to it. You might wonder, why don't we just, make it complex at the beginning? Why don't we just get the right answer first? And the answer, exactly. And the answer is because we're all human. It's very, very hard to get the answer right at first. And we all need money to eat and put a roof over our heads. And so when I go to the government, I say, here's my really simple approach. I'll make it more complex later. And then they'll give me money for 3 years, and I do the simple thing. And then 3 years later, I need more money for food, and then I do the complex thing. You'd think it's a scam, but we don't make a lot of money, so it's not really a scam. The other magic we can do with seismology is measure the core. So the core is pretty interesting, and I just wanted to show this image because it's really cool to me how we're using the exact same techniques that this old ham person made over 100 years ago to measure the outer and inner core of Earth, and we're just doing similar things on Mars. And what we can see just by doing some of that fancy stuff about which, where the S waves don't make it, those up and down waves, remember they don't go through the liquid core, and where these P waves make it through, these pressure waves, we can actually measure the radius of Mars's core to like quite a bit of precision. 1830 kilometers plus or minus 40 kilometers is pretty good measurement for something that's like on another planet like 2,000 kilometers deep. So this is kind of the magic of seismometry, and this is some of the stuff we learned using InSight. Now what's really cool is we got some of that information from some of these close by Mars quakes, the ones in the Kerberos Fossae region. But a few years later, we finally observed some really distant Mars quakes. One of them was actually due to a meteor impact, or asteroid impact, which is really cool because it's this weird looking Mars quake. This is S1000A. And everyone was looking at this data and they were like, why does it look like this? This looks really weird. This doesn't look like any Mars quake or earthquake. And then some other people took a look at these high resolution images that we get of Mars's surface every like month or so. And lo and behold, there's a new like, I want to say like 30-meter or 50-meter hole in the surface. And that's how we know exactly where it is, because it's like you can time that and see that that impact on the other side of the planet made enough noise and enough shaking in the planet that we could measure it. And not only did it make enough noise that we could measure it, but it was so far away that it went through the core, and that helped us even better refine our measurements of the core. So this is really cool because it's just like a random event. It's just a meteor impact, and then we measured it, and that really helped us out. On Earth, I think back in the day, they used to do something similar by setting off like really large dynamite explosions on the other side of the planet. But we can't really do that on Mars, so we got to wait for, asteroids to do that for us. But it's really awesome that we can just like measure that. And then finally, there's the magnetic field of Mars. So back in like 2006, we measured from space some of that fossilized magnetic field on Mars's surface. It's not there anymore, but it left an imprint on the surface. And these are some of the lines. The red is positive, the blue is negative, north and south, whatever you want to call it. So we knew that in the past Mars had a magnetic field, but we didn't know how long ago it shut off. InSight had a magnetometer on it. It turns out this is the first time we ever put a magnetometer, something that measures magnetic fields, on the surface of Mars. And it measured these magnetic fields that were 10 times stronger than those measured from space. So what that tells us is there's a lot of interesting things going on closer to the surface that we just can't see because our resolution is too low when we're out in space, right? This is really smooth. These are really large blobs. But if we had magnetometers on the surface, these blobs would be a lot smaller, but they'd be a lot brighter. They'd be a lot stronger. And that's just a real, complex way to say that Mars had a very strong magnetic field in the past, and that helps us figure out exactly when that magnetic field shut off, which can also help us figure out exactly when Mars lost its atmosphere, which in turn can help us figure out exactly when, potentially, Mars became uninhabitable. So finally, and I believe this is the last point, there's the mole. So this is the last thing, and this is actually really relevant to my research. I study this kind of stuff, the temperature as a function of depth in the planet. So I was pretty stoked for this bad boy. But what InSight did was it dug a little hole and put a little heat flow probe so it could measure the temperature as a function of depth near the surface, but underneath all that like dust and stuff. So in the actual rocks. This is really exciting. It was a whole third of the instrument. But it turns out that Mars rocks are like a little harder than we thought they were. And the mole just could not break through the rocks. And so sadly, the mole failed. We got no data. Although I do like the lead investigator, the lead designer of this said, we've learned a lot that will benefit future missions that attempt to dig into the subsurface. So that's what maybe like $5 million got us. But if that means that the next time we send it, we know the rock is like a little harder, so make your drill like a little stronger, and then we get good data, like maybe it's worth it, hopefully. But meanwhile, I sit here without any data for my research, so is what it is. So what have we learned? Again, right, like it's all about this InSight, right? This instrument. What did it do? What did it tell us? It told us that Mars is mostly done. The fact that we only observed Mars quakes from a few regions on Mars tells us there's not much going on the entire planet, but there's really interesting things going on in certain tiny areas of the planet. We learned that the large core means that Mars doesn't have lower mantle minerals equivalent to Earth. I kind of didn't talk much about this, but Mars's core is so much bigger than Earth's that it kind of takes up a lot of space that should belong to the mantle. And that's got a lot of implications for Mars being different from Earth. And then we have even more fuel for our hypothesis testing engines. So every little point of data matters, right? Every time we get like another number, it's always worth it, because even just one number after decades and decades and millions, tens of millions of dollars, getting one number really matters, because that gets us so much closer to understanding exactly what was going on this planet that is hundreds of millions of miles away, 4.5 billion years ago. We can figure out what was happening there. And in my opinion, most importantly, we can figure out whether other things were living there and answer, the age-old question of whether we're alone in this solar system itself. So that is my talk, and I'm happy to take any questions. Yeah, so the question is, how is the magnetic field frozen into something? So essentially, what happens is, let's say you have a magnetic field. It's happening. You've got, like, you can imagine even a bar magnet. And then some magma erupts. Magma's got a lot of iron in it, and that iron wants to be magnetized. So because the rock is liquid, it's easy for that iron to, like, move around to align with the field. Once that rock solidifies, you fossilize or like solidify that magnetic field, and all the iron stays oriented in that direction. And now it's producing its own magnetic field, because it's like a bunch of tiny little magnets that are all oriented. So once the actual magnetic field shuts off, we can still measure this tiny little magnetic field. And we can see that on the Earth, actually. And that gives us evidence for the fact that Earth's magnetic field has flipped upside down every, 20 million years, 30 million years. So yeah, it's pretty cool. I'll just work my way up from here and then back, snaking around. How much time do we have? Okay, yeah, that sounds good. Yeah. Yeah, so the question is there a relationship between the mass of the rocky planet and the tectonic activity? I think there probably is. If you've got a bigger planet, then it's probably got more radioactive elements. These are heat-producing elements, and those can power the engine of tectonic activity. And so this could be why, even if Mars had tectonic plates in the past, it doesn't have them anymore, whereas Earth still has them, because Earth is a little bigger. Now, the question is, Venus doesn't have them, and Venus is the same size as Earth. And this is why it's nice that we've got 3 rocky planets in our solar system. I don't consider Mercury to be a planet. Hot take, I guess. Thank you. It's so brave. But it's cool that we have 3 rocky planets in our solar system, 2 of which are the same size, and 1 of which is a little small dude, because that can help us investigate, what's the influence of size on these kinds of phenomena. Yeah, back, and then I'll snake around. Yeah.
You mentioned that the loss of the magnetic field was linked to the loss of the atmosphere. Is there any kind of mechanism for that?
Yeah, so magnetic field, or the question is, what is the mechanism between the link of the loss of the magnetic field and loss of the atmosphere? So this is actually kind of a spicy question. I think traditionally, the idea has been you need a magnetic field to protect an atmosphere, because the sun is screaming at us all the time with these really powerful ions that, if they hit our atmosphere, would blow it away somewhat. And the idea is the magnetic field shields us from those ions. Now, recently, I would say in the past decade, I think Megan could probably speak more to this, not to put you on the spot, that's a more controversial question, because maybe the magnetic field directs all the ions into one specific portion of the atmosphere, the aurora borealis or the aurora australis, if you're in the southern hemisphere, which none of us are currently. And potentially, by focusing all of that, it makes it easier to lose your atmosphere if you have a magnetic field. So, it's completely opposite whether the magnetic field helps or hurts. But that's science for you. It's always, it's either big or it's small, And maybe by learning more about Mars, we can figure out whether having a magnetic field helped it or hurt it to lose its atmosphere. Yeah, 1, 2, 3, yeah. So in the middle-ish, you, yeah. Yeah, so the question is, have they found any fossils on Mars? Any fossils of life? The answer is no. That'd be really cool. We haven't found any fossils. We found evidence that there was water on Mars. We found mudstone and clays and stuff like that. But inside those clays, we haven't found a little dude or a little guy or something like that. So, what? Oh, the meteorite. So this is a fun one. So there's a meteorite that hit during the 90s, during the Clinton administration, which I was talking about earlier, but only to 2 people. A meteorite from Mars hit Earth, and some people looked at the meteorite and they looked at these images and they were like, whoa, this looks like life. This looks like, one of them looked like a little wormy, another one looked like a little thing, I don't know. Imagine a microscopic organism, right? But it turns out that those were actually just minerals. And they were way too small to be living things. And also, you can make stuff from minerals that look like life. There's a great image that I didn't put in my slides. But the best part about this is someone misinformed Bill Clinton, and he gave this big old speech to the whole country and world, and was like, there may or may not be evidence that we're not alone in this universe. It's very funny, very X-Files. I think if you've ever seen Contact, there's a part where Bill Clinton is giving a speech in the movie. That's from the discovery of this meteorite. They didn't get Bill Clinton for Contact. And it's funny because we made a mistake, and it's funny to laugh at Bill Clinton. But but it's kind of an interesting, we learned a lot from that mistake, and that mistake gave us astrobiology as a field, because people were embarrassed, and we were like, maybe we should create standards of evidence. Maybe we should be able to, ask really difficult questions of things that we call life, rather than just willy-nilly going to the president of the United States and saying, hey, we discovered life. And so that's kind of interesting. And now astrobiology, we have a lot of these kinds of things, and you'll still see news articles that are like, we discovered life. But they're typically a little more cautious because the scientists are also just a lot more cautious. I have time for 2 more questions. Okay. There's one in the far back and then one really close. Yeah, so the question is, how do we know where all the fault lines are? And that's a really good question. I too asked this question when I saw that image. And I didn't read the paper that it cited. So I think what you do is, and man, geologists are wild, I think what they do is they just stare at these images of Mars. And we've got really high-res images. I'm talking meter or sub-meter resolution images here. And we just look at them, and we're like, that looks like a crack. That looks like a crack. That looks like an escarpment. Oh, that looks like a hill. That looks like a little thing. And these geologists have spent 30 years doing this, right? Mostly for Earth, right? On Earth, we see similar things. And I think when you just spend 30 years, just looking at pictures of a planet, your brain just kind of works that way. Now, I don't know what geologists sacrifice to get there. I don't really want to know. I'm not a geologist. I do respect them. They do a lot of good work. But I think, yeah, that's it. They just said these are the faults. And they're mostly right, I think, based on the fact that we can look at some of the faults that they recognize as faults, and we can identify the earthquakes from them. But yeah, that's mostly it. You just look at pictures and you're like, that kind of looks like a thing. And then last question.
How do we know what happened if there was an atmosphere and how dense it was? So was that trying to be inflated?
Yeah, so the question is, how do we know what Mars's atmosphere was like, 4 billion years ago? And the answer, is, again, actually is these Martian meteorites. So we've got a few other Martian meteorites, not just ALH 84001, which is the Bill Clinton one. We've got a bunch of other ones that are all really, really old, like 4 billion, 4.3 billion years old. And inside these meteorites, they got these little gas bubbles. And when we poked open those gas bubbles, we measured the gas, we're like, this is like ancient Martian atmosphere. And that's actually how we can tell that they're from Mars today, because we compare those little gas bubbles to the atmosphere of Mars today, and we're like, oh, it's like the exact same composition, or like it's got the exact same isotopic signature, which is the whole thing. It's like a fingerprint. And that tells us they're from Mars, but it's from way back in the day. So we get a better idea of like, hey, maybe this was there. And it's a lot of guesswork as well. Cool.
You can just skip
Oh,
it.
yeah.
Okay, that was fantastic. We can give Rudy another round of applause. Hey, Rudy, can I have the clicker?
Can you help me?
Oh,
It's
amazing.
Like,
Okay,
it has a little clip.
so we have one first place trivia winner that got 8 questions right. Yes, we have 2 second place trivia winners that got 7 questions right. And we have 1 third place trivia winner that got 6 questions right. Okay, before I announce the winners, I'm going to go through the answers, per usual. Okay, the Mesopotamian name for Mars was Nergal. That is the planetary symbol for Mars. It is true that pieces of Mars have been found on Earth. Those would be meteorites. The Amazonian period is the period that Mars is currently in, as Rudy told us. 687 days makes up a year on Mars. Viking 1 was the name of the first spacecraft to successfully land on Mars. Areographers Johann Madler and Wilhelm Beer drew the first map of Mars. It was not map maker 1 and 2. Carbon dioxide composes 95% of Mars's atmosphere. It's false that a meteor would burn up more rapidly in the atmosphere of Mars because Mars has a thinner atmosphere. And 8% of schools in the juvenile justice system offer physics classes. And we're going to learn more about that with our next talk. Okay, so our first place trivia winner with 8 questions right was Novo. Yeah, well done. Okay. Our first second place winner that got 7 questions right is Skycar. Who's that? Our other second place winner is Simcoe's Choice. Nice name, by the way. Okay, and our third place winner with 6 questions right is Doja. Well done. Nice. Okay, so if you won trivia, you can come at the end of the second talk to get a prize. For now, we're going to take about a 10-minute break for people to go get more beer, go to the bathroom, and then I will introduce our second speaker. Thank you.
Is your mic live already?
I don't know. I'm assuming so.
Y'all can have the rest of the fries.
Joe's like, I don't want your charity fries.
Well, you're getting my trash fries.
Cycle dogs, I will end you. I'm so hungry.
I think my phone's not working.
I can call them and ask if they got our order.
Try not with that.
I want to know if it's coming or not.
I bet it is. It looks like other people are looking around.
I'll just just double check.
I would prefer that.
Now would be a great time for it to arrive so I can eat before I have to talk.
Call and ask if you want that. I'm just I'm upset about my phone. My phone's not working. Yeah, apparently.
If you connect to Wi-Fi,
Oh, that makes sense. Yeah. Do you usually come to these or? Okay. I was gonna say because I've been doing these both months for like a year, so if I just hadn't seen you the whole time, I would be very disappointed.
hey, we put in an order online. I just wanted to make sure that it actually went through. It should be under Joe or Joseph Janizek, Janizek.
I currently live it is really pretty.
Okay, thank you so much. Do you happen to know like an ETA or anything on it? Yeah. Oh no, I'm sorry. Okay, I see. Okay, thank you so much. They said pretty soon. The very specific. They said they got overwhelmed because everyone ordered food. We did though. We got her like 6:40.
Yeah, I know.
So I bet we're in the second delivery that they said is coming soon.
I should have ordered right away. I guess I took usually didn't order until almost.
You ordered before people started showing up, I felt like.
No,
Please have some
I
fries.
delivered. You excited to talk?
No, excited to be gone.
It's gonna be great. I'm really upset about my phone. I don't know what's going on.
Are you not getting texts? Do you want me to try texting you?
Go to text me.
Send this text message. Can I see?
Yeah, I got that.
That's weird.
Maybe my wireless carrier just said enough is enough. Can I see what yours says?
Where?
General. I think I got him like cellular. Because like I got like scroll. Your thumb is just you're like
Sorry, I don't know.
you're like I don't see it.
Oh, stop!
You're like where is it?
Stop! Let me see.
Where is it?
Stop! How does it
Scroll.
compare?
Or you want me to scroll back up?
Stop it! What are you looking to compare?
The cellular data over the current period.
I mean, yeah, you have a lot more than me.
Only like a terabyte. I don't know.
Only like a terabyte.
Could you send me a second?
Oh yeah.
Alright, got it. So I'm at least getting a text message.
He gets
I don't know. That's bad.
a free
But how would you Google it?
I don't. I'll just figure it out later.
Starting an understanding.
I've done that twice.
Okay. Sorry.
Don't worry.
with his salmon
You
oil
wanna
and
go up?
his bone broth.
It's still the
and
break.
his little like salmon emitter. He's just so good. I just love it.
I'm excited.
Oh, I finally got your iMessage.
Well, that's good. Man. Everyday thing, Kim.
No, an everyday thing. Okay, well, so he has to eat like his prescription for the rest of his life. He's had it for 2 years now, and he hasn't had any health issues. And I'm like, this is just so sad. He just has to eat his food for the rest of his life. He deserves for it to be spiced up. So I did a bunch of research. He can have a raw diet on top of it, which is what he deserves. His little
I
soup.
do not want to.
And he loves it. He eats it all the time.
You will. You will meet and you will freak. Man, it really started pouring rain. Kathleen and Mia had to get up and eat somewhere else.
Oh wow.
But I just don't know if we're there. He's had so much change with moving in.
Look how wet the bench is.
I see it. Sorry.
November 18th. But we're not celebrating it on that day because Alex can't make
I
it.
don't know. Megan's friend.
So we're doing it.
Why?
I like it.
Yeah, it's funny. They just, I think it was like meant to be like a placeholder. And it's just like, oh, my friend made this and like 2 seconds and we've just been using it forever. I like it. Oops. Sorry.
It's got a real layer to it.
Will you guard my bag? It has my laptop in it. Are you listening?
Yeah, that has a lot.
Please, and will you guard it? I'm not going to the class. I'm going up there.
Okay, you got it. Oh, okay, good. Good.
Oh, thank you so much. Okay. Where's the laser?
The what?
The
Oh,
laser.
I think it's yeah. Yes. And feel free to announce the stickers if you during your talk. Or I can say it after. It's up to you. Okay. Okay. Welcome back, everybody. Hello. Thank you. Okay, so at this time, it is my pleasure to introduce Samantha Gilbert-Janizek. She is also a graduate student at the University of Washington in the astronomy department. And in addition to research, Sam is also involved in a number of outreach opportunities. So she's going to tell you about one of these opportunities today called Raising eSTEAM, which in our case stands for Science, Technology, Engineering, Astrobiology, and mathematics. And so this program, was that me? This program brings tutoring and science experiments to incarcerated students in Snoqualmie, Washington, and I will let Sam describe the rest of it. Bring it.
Hello, can you hear me okay? All right, hello, good evening. Thank you for being here. So like Megan said, my name's Sam Gilbert-Janizek. I'm a 5th year PhD student in astronomy and astrobiology at the University of Washington. And most of the time you'll find me working on my research, which has to do with predicting our ability to accurately interpret and recognize signs of life if or when we do encounter them on planets outside our solar system. But tonight, I don't really want to talk about my research. I actually want to talk about something that I've been doing more in my spare time with some of my fellow PhD students. And like Megan said, that is bringing astrobiology to incarcerated youth as part of an initiative called Raising eSTEAM. But to start off, I want to talk a little bit more about astronomy and its importance to humanity. So kind of zoom out and think a little bit more abstract. So I believe that humanity's relationship with the night sky is fundamental and innate. And what I mean by that is that we have always peeked out at the night sky, we've always observed our little slice of the universe, and we've always asked questions. That has always been true. And I believe this is as innate to us as a species as music or arts or language. And we have evidence to support this across time, across space, and across cultures. So for example, I'm showing you here a star map carved into a mammoth tusk found in present-day Germany, carbon dated to be about 33,000 years old. And it's thought that it depicts the constellation Orion, 33,000 years old. In Egypt, a 7,000-year-old stone astronomical calendar was unearthed. 7,000 years old means it would be about 2,000 years older than Stonehenge. And people would have used something like this to predict the seasons for things like farming and other sorts of activities. 2,000 years ago, a Babylonian astronomer looked up into the night sky and saw what we now call Halley's Comet streaking across the darkness. And he wrote down what he observed, just like any good scientist would do. It just happens that the form of writing they had at the time was chiseling cuneiform into a tablet. And so we found that as well, and were able to translate it. Finally, about 1,000 years ago, the Maya erected a dome-like structure in the city of Chichen Itza. Archaeologists aren't 100% sure what the structure is, but it just so happens that it has direct sightlines to 20 different astronomical phenomena of interest and importance to the Mayan people throughout the year. So I think what we're looking at here is a Mayan observatory. And this isn't just an ancient phenomenon either. Today, people come together all the time en masse to experience astronomical events and phenomena together. For one example, not so recent, the Leonids are a meteor shower that occurred just about every November. And in 1833, they were particularly spectacular. And we know this because there's all kinds of written accounts and art as well. This is a wood cutting depicting the meteor shower that exists that describe this event. And it was particularly spectacular because you could see hundreds of thousands of meteors streaking across the night sky. It said that there were so many meteors that it illuminated the night sky as if it was daytime. Tons of people noted this meteor shower. So for example, the Cheyenne signed a peace treaty while this event was occurring, and the Lakota restarted their calendar to coincide with this meteor shower. Multiple enslaved people also left behind accounts of witnessing this meteor shower, including Harriet Tubman and Frederick Douglass. And it also inspired what I think must be one of the very first citizen science projects. A professor at Yale, Dennis Olmsted at the time, took note of this event. It was visible all over North America, and he put an ad out in a newspaper saying, hey, if you saw this, send me your story, let me know what you saw. He collected these crowdfunded stories, and using them, he actually published a scientific article the following year. For a more recent example, of course, in 2017, we had the total solar eclipse, which was visible across 14 states in the United States, spanning from the Pacific Ocean all the way over to the Atlantic. Tons of people traveled to see this. I'm sure some of you in the audience may have traveled to see it. Show of hands. Lovely. Yes, yes. I'm very jealous. I didn't get to see it. Yeah. It's sick. It's awesome. And I think the next one might be in 2024. Yes. So make sure you go and see that. I definitely will be making a special effort to go see it. So it's estimated that 215 million people witnessed totality. This is more than double the number of people who typically watch the Super Bowl in a given year. So I think we can finally settle it. Astronomy is more popular than football. Unfortunately, not everything that we experience collectively is positive. So as I'm sure everyone here remembers, in 2019 and 2020, the world came to a grinding halt due to the COVID-19 pandemic. And during this time, for months on end, we only got to see our friends and family and loved ones on our laptop screens. We sanitized our groceries. It made sense at the time. And we picked up weird hobbies to pass the time. And as we all locked ourselves inside our homes for our own safety and for the safety of everyone around us, we experienced really intense levels of isolation. One of the places where isolation became really especially severe was actually in US prisons. So at the peak of quarantine, when every day was blurring into the next, I would do the same thing every morning, open my phone, look at the news app, scroll through the articles. Is this pandemic ever going to end? Do we have a vaccine yet? So on and so forth. And I would also see articles like this, talking about what it was like to experience the COVID-19 pandemic from within the walls of one of America's thousands of jails and prisons. And I learned that COVID-19 isolation was particularly intense for incarcerated people for many reasons. First of all, a majority of prisoners are held hundreds of miles away from their homes and their hometowns, so that would be pretty isolating even outside of a pandemic. But even worse, visits, programming, and physical activity were all completely canceled when COVID-19 started happening and quarantine happened. So even though your family could theoretically call you up and check in with you, we also know that telecom companies charge exorbitant rates for phone calls into prisons. And as we know, one of the biggest impacts of the pandemic was really detrimental to the financial situation of millions of families across America. So what this all tells us is that with prisons, COVID took a bad situation and made it even worse. Research shows that consistent family visitation is something that's correlated with prisoners not recidivating, meaning once they get released, they never go back to prison. So if they're not getting visits, that means recidivation is higher. That means that people are not getting the support they need in order to leave prison once and for all. And this doesn't just affect the prisoners, right? It affects their loved ones outside prison as well. So Smithsonian Magazine reported in 2019 that nearly half of Americans have a close relative who's been incarcerated. So that means nearly 1 in 2 people in the US is directly impacted by the prison system. If you yourself are not directly impacted, that means you probably know someone who is. And honestly, that tracks. We know that incarceration is a massive industry in the United States. A 2021 study shows that the US incarcerates more people than any other country in the world. And unfortunately, this is a superlative that includes children who are also incarcerated. So if we break it down by the numbers, we can see here that incarceration rate per 100,000 people, the US is completely off the charts compared to places like the UK, Portugal, Canada, and France, and other countries as well. And you might think, well, there's 50 states, all the states have their own institutions. Even if you account for individual states, this phenomenon still occurs. So if we treated Washington state like it were its own country, it's still enormously off the charts in incarceration rate, more than triple times the rate of its nearest neighbor, which would be the United Kingdom. And in Washington specifically, about 1/3 of that yellow bar you're looking at is children. In total, 66,000 children in the United States are incarcerated. No, actually. We'll get to that, but some of these institutions actually do hold on to women up to the age of 25. I'm not sure how often that happens. It's usually a very small segment of the residential population of these sort of facilities. But yeah, by children, I'm generally talking about 18 and under. Yeah, thank you. And much like other American institutions, we know that incarceration isn't equitable. Black youth are 4 times more likely than their white counterparts to be incarcerated. Children in prisons, just like children anywhere else in the United States, have a protected right to an education. But from the minimal studies that we've done on education in these sorts of environments, we know that it's probably not cutting it, and it really doesn't measure up to the sorts of education that children outside of prisons are getting. In fact, Professor Peter Leone from the University of Maryland said, The educational services and programs in prisons are not something you would tolerate for any of your children. And this is for reasons like the following. In juvenile facilities, school is frequently canceled. Understaffing is a tremendous problem at places like this. You may have read articles about it in the Seattle Times. And if not enough security people show up, if 1 or 2 people call in sick, school is just canceled for the day. The kids don't get to learn. When school does happen, school staff are usually inadequately trained to support students who have learning disabilities and other sorts of special needs. And it's estimated that up to 70% of children incarcerated in Washington fall into this category. The classes that are offered in youth prisons do not measure up to those in public schools. So here's our trivia answer. While 60% of public schools in the US offer physics classes to their students, only 8% of schools in juvenile prisons do. And when the education is lacking, this has severe impacts down the line. So in 2015, almost half of all children incarcerated in Washington recidivated, meaning they were released and then they went straight back to prison again. Even if they don't recidivate, even if they do manage to leave these facilities for good, 2/3 of incarcerated children never return to school after they leave juvenile facilities. And that translates to very limited opportunities later in life when they might try to obtain gainful employment and sort of stay on the right track and not go back to prison, right? So me and my fellow PhD students at University of Washington, we noticed this phenomenon, we started talking about it, and we decided that we wanted to try to leverage our advanced degrees, our love of learning, our teaching experience to try to build a bridge to incarcerated children nearby us. So in 2021, myself and my fellow grad students founded Raising Esteem. So I'm sorry, it's kind of an unfortunate pun on like raising self-esteem, but it's also an acronym because of course, and it stands for, Megan was saying earlier, raising education in science, technology, engineering, astrobiology/art, and mathematics. So a little bit about us. We are UW astrobiology PhD students. Some of us are astronomers, some of us are geologists, some of us are earth scientists. And we offer one-on-one tutoring as well as hands-on science activities to incarcerated youth at Echo Glen Children's Center, which is a juvenile justice facility in Snoqualmie, Washington. It's about a 30-minute drive away from here when there's no traffic. Just as a summary of the facility, Echo Glen has about 100 children. Boys are ages 11 to 17, girls are as young as 13, and as I was sort of mentioning before to this gentleman's question, a very small handful of the residents are women up to the age of 25, maybe like 2 or 3, honestly. In the last couple years, all of us combined have cumulatively spent hundreds of hours tutoring at Echo Glen. And we've tutored students in subjects including, but not limited to, financial math, geometry, biology, chemistry, Spanish, language arts, health and wellness, as well as career and post-release advising. And spending cumulatively hundreds of hours at Echo Glen, we have personally witnessed and learned so much more about the challenges that face children in the prison classroom. So for one thing, a good chunk of the coursework is actually done independently online. There are course instructors only in the sense they sort of grade the students on completion. There aren't any pre-recorded lectures. There aren't any live lectures. The students are responsible for teaching themselves. Even worse, the computer lab, where up to 15 students are working at a given time, is extremely noisy and has frequent distractions. It's an impossibly difficult environment to think in, let alone to try to do your classwork in. And believe me, I know this because I've tried. Additionally, students have incredibly limited resources to support learning independently. There are no reference books in these computer rooms. There's no Wi-Fi. They can't Google something if they don't know it. And it's frequently difficult for students to obtain simple things like calculators, protractors, compasses in order to do the work that they need to do. They're also not really permitted to access their work when they're in their residential areas or like in their rooms. Like, most kids go home at night, they do their homework in their room, and that's where a lot of learning happens. These kids don't get to do that. And they don't get to hold on to tools like pencils either, which would also make it very hard to do your work. And lastly, Echo Glen, of course, is not just a school, it's a prison, and it's a state facility. So that means you have multiple layers of authority that the students have to navigate on any given day. And these layers of authority rarely communicate well with each other. So you've got security on the one hand, Washington State employees who usually staff the residential areas, and then you've got school employees and teachers, and they all function independently, and it can lead to a lot of dysfunction that only winds up hurting the students. So for example, one of our tutors personally witnessed a security person throw a child's schoolwork into the trash to punish them. So the message that all this sends is that education is really incidental to the juvenile prison. And what I mean by that is that the main purpose of a place like this isn't necessarily to educate and thereby rehabilitate, it's to punish. Effective education could really help these kids get on the right track and improve their lives, but effective education simply is not happening in the prison environment. Kids who likely already struggled in school are further alienated from their learning and their education in a place like Echo Glen. Given these circumstances, we wanted to go beyond tutoring and see if there was more we could do to make learning fun and engaging and safe for these students. So as astrobiologists, we study life on Earth and its propensity to exist elsewhere in the universe. And so we spend a lot of time thinking about really resilient forms of life that can adapt to even the most challenging environments. So if you know where I'm going with this, it's not the biggest stretch in the world to imagine that a kid in prison could relate, to something like a water bear that's thriving in really difficult circumstances. And they might relate to this field of study. So over the last year, we have implemented 7 unique hands-on astrobiology lab activities with students at Echo Glen. These activities included creating crystal gardens, observing the sun through a telescope, recreating the Mars Viking experiments, which Rudy referenced a little bit earlier, creating our own galaxies in milk and soap, sharing a mobile planetarium show, simulating impact events on Mars and the moon, and learning how to do reflectance spectroscopy. That last one was kind of the most ambitious one. So we don't have time to talk about all these activities, but I do want to share about just a couple of them. So first we'll talk about crystal gardens. So in this activity, kids get to watch crystals that appear to grow right in front of their very eyes in a test tube over like a 15-20 minute period. So if you look towards the bottom of the video, in this sort of white rectangle I've highlighted here, we've got metals at the bottom of the test tube that appear to be growing upwards. So if you see these little blue tentacle thingies, those are actually growing upwards over time. And they'll reach higher and higher and higher the longer you wait. And same with this guy over here, it kind of grows more as like swirlies. This one's hard to see because it's really white, but if we had a darker background, you could see these sort of like spindles growing up as well. And similar with this green guy over here. So what's really cool about these gardens is that they're actually not alive at all. The crystals appear to grow solely because of a pressure gradient inside the test tube. And so we use this as an opportunity to talk to the kids about why astrobiology is so hard, why it's challenging to differentiate living processes from non-living ones, which is sort of the biggest challenge we face in searching for life in the universe. It's also a great opportunity to talk about how you can't judge a book by its cover, and things are frequently much more complicated than they seem. Another activity that we did was observing the sun through a telescope with a special solar filter. Megan supplied the telescope. So we had the students draw what they observed. And so here's kind of a collage of multiple of the observations that we collected from the students. And some commonalities amongst these recorded observations. You'll see that there are sunspots in the photosphere that the students observed. And some students even noticed this phenomenon called limb darkening, where the outer edges of the sun appear to be darker than the inside. Sorry, it skipped. Oops. And so we use this lesson as an opportunity to talk about, our closest star, what it does for us, how it's important for life, how it challenges life. And then we also related that to stars in other solar systems and how those stars might affect life that's potentially trying to grow and survive on other planets. So in the future, we really would like to do more of these activities. We want to repeat some of the ones we already did this summer, and we want to come up with even more ones. And it's always an exciting challenge navigating the prison system and security to try to bring these sorts of activities to Echo Glen. Just as an example, I think one of the materials they freaked out the most about us trying to bring in was a Sharpie. So there's a lot of challenges to navigate there. We'd also like to work on bringing guest speakers to Echo Glen. I've actually been in contact with a few scientists who are formerly incarcerated, meaning they went through similar experiences that these kids are going through and still managed to make it into a career in science. And so I'd love the kids to be able to hear their stories. And while we've been focusing a lot on sort of bringing our energy to Echo Glen, I think it would be really cool to work on making the relationship a little bit more mutual with UW. And talking more about our work and the kids that we work with at Echo Glen at UW and bringing more awareness to that there. If this work excites you and you're wondering what you can do to help, first of all, thank you. I really appreciate it. You can always spread the word. The reason systems like this never change is because people don't know and people don't talk about it. I'd also recommend looking into the prisons in your area, learning about the kinds of people who are incarcerated there, the challenges that they're facing, and what those institutions are doing to support prisoners to get on a better life path when they leave. If you're still wondering what you can do, I would love for you to reach out to us. I'm going to show a website link on the next/last slide where there's a contact form that you can reach us through. And we also have some stickers to give away as well. Come see Megan and Sam after this talk if you would like to grab one. So on our last slide, now I'd like to thank our generous donor, Autodesk. And as a final thought, I also wanted to share this quote from Mariam Kaba that really sort of encapsulates what motivates me to do this work. And that is, hope is a discipline. And to me, what that means is it's not enough to pray a better world into existence. We have to work and we have to struggle every day to make that a reality. Thank you so much for your time. I'll take some questions now, folks. Got them? Yes. Sorry, you can go first. Yeah. Or sorry, you in the high vis. Yes. So the question was, what do you say to students who don't have a lot of self-confidence, who think that because of their circumstances, because they're in prison, that they can't do something like astrobiology? So, unsurprisingly, the students normally don't directly say something like that, but you can tell in their demeanor that they're very closed off. And I think our approach to that has just been to be very consistent. We keep coming every week. Even if a student didn't really want to work with us the last week, we're right back in that classroom the next week. And we show them that our support isn't contingent. We're there to help them no matter what. And I think by solidly doing this work for the past couple of years, we're really starting to build that trust. And we've had students open up to us in really meaningful ways, and that's been really beautiful. Thank you for asking. Yes? So the question was, what needs to be done at a state and national level to prevent more students from being stuck in the system? That's a big question, right? Like that has to do with a lot of other institutions, a lot of other structural aspects of American society. God, that's a hard question to answer, and I wish I had some ideas for you. I think for me, I try to focus on what I can do myself as an individual. And that's why this program really came into being. Our expertise is science, our expertise is astrobiology, but we still think we can use it to make the world a better place. It's not just thinking about things that are far off and irrelevant. It's actually very relevant. It can be very inspiring to kids who are struggling with things like this. Yes? Yes, the question was, do we teach both young men and women? So far we've actually interacted mostly with boys. I think this is because we come in the mornings and the girls are really hard to rouse out of bed, so they never quite make it to the classrooms when we're there, but we're working on that. I think Sam has worked with a young woman consistently for a while now, and we've done some activities with them now as well, some labs after school. So we are working on reaching the girls as well. Yes. Okay, so the question was, how difficult was it to get Echo Glen to agree to be a part of this? That was sort of the most interesting aspect of trying to get this off the ground. As PhD students, a lot of what we do is just kind of send cold emails out into the abyss to other scientists and just ask for things, just knowing that probably we'll get an answer that's like nice and helpful. So that was kind of an interesting part of this, because I think we also just sent some cold emails out to various institutions, some existing programs as well. There was an existing program that used to be nearby, but it moved really far away. So we wound up not collaborating with them just because we couldn't drive to that institution realistically every week. It's like a few hours away. So I think what we did is we reached out to a woman who already had sort of like a thriving volunteer program. She runs these things called socials, which theoretically anyone can go participate in. The kids get to do a craft or something like that. And work with volunteers, adults who come in and sit with them and do the craft with them and talk with them. And it's like a nice way for the kids to get some socialization with folks outside of the institution. So we reached out to her because we figured she must know what's up. She's been doing this for a while. And she was very helpful. She put us in touch with the right people. And then it was more emails, more Zoom meetings, more convincing them that we're not weirdos, and that we really have something unique to offer to the kids at Echo. And so far, again, like doing that work, starting by just tutoring, it built a lot of trust, not just with the kids, but with the staff at Echo Glen, with the security at Echo Glen. They know our faces now, they know who we are. And that was a really helpful foundation for expanding into doing like after school activities and more ambitious things, like bringing in materials into the prison. 2 more questions? Yes. Oh, I'm so sorry. Okay, you go first. Great question. So Oge just asked, do you plan on continuing to mentor students after they leave? So this is an unfortunate aspect that we haven't figured out quite how to navigate yet. There's a lot of laws, fortunately, that protect children, especially in institutions like this. And for a lot of reasons, they really don't want you contacting kids outside of the school context, which makes a ton of sense. So we haven't figured out how we can continue to support students in that way, but that's something that we're definitely thinking about working on, while obviously also like keeping the safety of the kids in mind.
So like historically with programs like this, my understanding is that students do better when they feel that there's an incentive or a reward, for their good performance. So is there going to be talk with the state and the prison system about taking kids who show real promise in these fields and saying, hey, this kid's really putting their effort into this, there's potential here. Is there something that we can do to shorten their sentence, provided that they go in and do their school studies? And kind of like what she was saying, is there something that you think to follow up on that? I know that the real prison system or the adult prison system, you get your college degree and that opens up the door for job opportunities. With these kids, it's kind of like they're learning stuff that's really cool. I think that they would benefit mentally from the idea that, hey, I can turn this into something, and they embrace that kind of, yeah.
Totally. Okay, so just to repeat the question, I'm going to try to summarize it a little bit. But basically the question was, are we working with the state and the prison to try to make this program more of an incentive for students? So, if you do this work, maybe your sentence gets cut down a little bit, and also you're exposed to more opportunities later. So I think our main strategy right now around that is to really focus a lot on career/post-release advising. So it might not surprise you, but most of what they focus on exposing the kids to in terms of careers has to do with the trades, right? So working with your hands, working in construction, so on and so forth. And there's nothing wrong with that, of course. But we thought it seemed a little unfair that they just weren't getting exposed to other routes as well, such as a more education-focused path that would take you through a college degree, for example. And we just wanted them to have that option too. So we've been talking to them more about careers in science, how you become a scientist, what it's like to go to college. And we definitely have some students who are pretty advanced students who wanted us to teach them calculus and stuff like that, way beyond their grade level, show a lot of promise. And once again, we hope just by working with them on a weekly basis, getting to know them, getting to know their interests, that we can keep them engaged and thinking about those potential paths. I think it might be hard to make something like this super official with the prison system. Once again, there's just so many different layers you have to navigate to get something like this to even work. And sometimes, you know, the state will have feelings about it, and then the security will have feelings about it. And it's just a very difficult thing to navigate. But I think that would be a great goal eventually, to try to build it more into the structure of their schooling. Yeah. All right, there's one last question. Do we have time? Okay, one last question.
Is that the only one that responded, or are there any of the prisons for you, the prison systems for you in the Seattle area, like more, like obviously like in the close vicinity here?
So the question was, did we reach out to any other prisons that have children in them in the area? So there's definitely a juvenile detention center downtown. I think that in our strategy didn't seem like the best target, just because kids tend to pass through there pretty quickly. So it might be hard to kind of like make an impact. Whereas at a place like Echo Glen, there are kids who are there for years, if not months. And so you get to see the same kids a little bit more consistently. But even then, there's still a ton of turnover, which is also something we're working on navigating as well. Thank you.
That was a great talk, Sam. I think we can give a big round of applause to both of our speakers. Okay, before I let you go, I just wanted to mention Astronomy on Tap next month will be on October 18th. That is the third Wednesday of the month. I try to keep them consistent on the last Wednesday, but we had to make an exception next month because for the first time, the astronomy department at UW has actually supported us in inviting one of their invited speakers to also come give a talk at Astronomy on Tap. So he will only be here for that Wednesday. That's why we had to do it. But he's going to be fantastic. His name is Christopher Moore. He's from the Harvard Center for Astrophysics. So you can look at our social medias to see the announcements for Astronomy on Tap next month, but it would mean a lot if you could show up and support that. Other than that, if you won trivia, please come get your prize. And what? And we have e-Steam stickers. If you want an e-Steam sticker as well, you don't have to win trivia to get one of those. And so with that, please get home safe, and thank you for coming tonight.
I was like, what am I doing? What are these hands doing? You just... Are they the stickers for the